All right, what can we say about why convex functions are so great for minimizing or why concave functions are so great for maximizing? So what do you think you can say? If a function is convex, what can you say about local minima and global minima? I mean, one of our big questions is, when should I be concerned about getting trapped in a local minimum that's not a global minimum? Well, you can prove, and it's not very hard, to prove that a convex function has no local minima that aren't global minima. So if you know the function is convex, then you cannot get trapped in a local minimum. And I've even got that as one of the exercises on the homework. That's for unconstrained problems. How about for constrained problems? Let's think about if the feasible region is convex. That's a nice place to start. So let's go try this grapher here. So I've got an objective function here that's a convex function. It's a bowl shape, or squished bowl coming up out of the screen at us. So here's the minimum. And I've got a feasible region here that is not convex. So let's go turn that into a nice convex feasible region. So where is the minimum of my objective function in this convex feasible region? Well, it looks like it's about here, right? Kind of the center of the last contour we see. It's exactly a quadratic objective function, so that should be good. So the minimum for this objective function is here, which is just kind of in the feasible region. That's fine. What if I move the objective function over, the minimum over this way? Then the minimum of the function itself would be here, but that's not feasible. Where would the minimum of the in the feasible region be? Well, probably about here, right? Let's try moving it up to make it a little more obvious. Where would you say the minimum is in the feasible region now? It's kind of as close as you can get to that. Would you say it's kind of the last contour before we leave the feasible region? And what can we say about that contour? It looks kind of parallel to the edge of the feasible region, so that's an interesting way to think about it. So here's the question. We said for an unconstrained convex function minimizing, we can't get trapped in a local minimum. Can I get trapped in a local minimum when I'm minimizing a constrained convex function on a convex feasible region, so the interior of this circle here? As I move my objective function around, well, the minimum there is, that's the global and local minimum. If I move back over here, do you see me getting trapped in a local min that's not a global min? That's the local min and global min for that whole feasible region, and anything out here is worse. So it turns out when the feasible region is convex and the objective function is convex, remember that's two different ways of thinking. When the feasible region is a convex region and when the objective function is a convex function, then again you can't get trapped in a local min that's not also the global min on the feasible region. So that's another great reason to love convex functions and convex feasible regions. But what about non-convex feasible regions? Let's go turn this back into a non-convex feasible region. What would you say is the minimum of the objective function on this non-convex feasible region? Take a sec to think about it. Well, it should be about here, right? The kind of the lowest contour we can get. So imagine this contour a bit over here. So that's your local min and it's a global min, because any direction you go from here, like that or that or that, you're going to be going uphill on these contours. Are there any local mins, though, in this graph that are not global mins? Take a sec to think about that. Yeah, over here, you're kind of trying to go downhill on these contours, and you just get to the edge of the feasible region and you stop. That's a local min, but it's worse than this one because it's a higher contour. So if your feasible region is not convex, there's all sorts of trouble that can happen. All right, another question is, well, what if we go back to a convex feasible region? And actually, let me switch to another one here. I've got one with straight sides. So convex feasible region, but what if I switch my function to be concave? And I can do that by saying I'm now going to use -1 and -3, -0.3 and -5. So my objective function just switched from coming up out of the screen at me to going down into the screen. And I'm going to throw a negative on here so I see all those contours. So it looks like it was before, but now it's going down into the screen, and this is kind of the mountaintop. So let's move this set of contours so it's intersecting the feasible region. So inside the feasible region is here. So what can we say about the minimum of this concave function? So it's now trying to minimize, so I'm trying to get the farthest away contour from the center. So where's that minimum going to be? Let's graph a few more contours here. I want to get as far away from that center as possible. So would you say it's here? Well, I could scoot along this edge and get contours that are, sorry, other way, right? If I start, if I started here and moved along this edge, then I'm going to farther and farther away contours, and I get here, and then if I start moving this way, then I'm going to contours that are closer to the center, and so the optimal point would be here. What if I move my objective function a bit? So just pretend I have a different objective function. Where's the optimum now? It's still going to be this point. And if you go this way from that point, you're going up the hill toward the mountaintop. If you go this way, it looks like you're going away from the mountaintop, but you're actually crossing contours that are getting closer and closer in height to the mountaintop. So the optimal point is at that edge, that corner point there. What if I moved my objective function down? You can see it's going to be pretty much the same thing, except now this will be my optimum point. Oh, wait, is that the optimum point? Well, if I move this way, I'm going up the contours. I'm more nearly touching this contour that's closer to the peak. But then if I keep moving, then I'm going down over here, down the contours until I get to that point. So in this case, that's my optimum point, not along the edge. So can we say now for minimizing a concave down function, then the optimal solution is at a corner point. We tried a few different cases. It seems plausible. That's actually mostly true, except what if I switch away from this linear linear edge feasible region and go back to this curved one? Actually, let's even make it a convex feasible region. So where's my minimum of this concave down function now? Maybe it's not shown super well because I'd keep moving away from the mountaintop, so I want to keep going out and out along these contours. So let's show a few more contours there. Maybe we'll do something like that. Okay, and we'll show more contours. There we go. So again, we want to get away from the center here. So where's the optimum point going to be? Somewhere right around there. And would you say that's a corner point to the feasible region? Well, the feasible region doesn't really have corner points now, does it? But it's not in the middle of the feasible region. It's not in the interior. It's kind of on the border. But back when we had this, the optimal point was not on the border. It was at a corner point. So how can we talk about borders and corner points for curved regions? So it turns out there's a word called extreme point. And we just said this. If you're minimizing a concave up function on a convex region, can't get trapped in a local min. If you're minimizing a concave down function, which is what we were talking about more recently, then the optimal solution will be at a corner point or an extreme point if their feasible region has curved borders. So an extreme point is a point where any feasible line segment that goes through it has that point as a endpoint. So imagine any point on a circle for a feasible disk, then any point, any line segment that touches that point on the edge that stays feasible has to have that point as an endpoint. So that's an extreme point. So minimizing concave up functions, no local minimums. Minimizing concave down functions on a convex feasible region, then the optimal solution will be at a corner point or an extreme point, and we can get, and often do get, local mins, local things that aren't global. So two good things to know about. And in the next video, we'll look back at some previous problems.